Okay. I just now noticed that it's almost 11 o'clock here in Greece and I suppose in Lithuania. So let me make some preliminary remarks. Good morning to everybody once again. My name is Panayiotis Frangos from the National Technical University of Athens, Greece, School of Electrical and Computer Engineering. And let me give, if you permit me, to some obvious instructions. So in this session 11A, which is in signal technologies, we will have 5 presentations. And since the total duration will be 1 hour and a half, I would like, please, the presentations, including discussions and possible questions, to have duration 15 to 18 minutes at most. 15 to 18 minutes at most, including discussions. So if you permit me, I will try to be a little bit strict about that in order that the organizers have a correct schedule following to our session. At some time, the closing ceremony will take place. So I would like to be correct in the timing. So please allow around 15 minutes per presentations, including discussions, 18 minutes at most. So now I think I can start the session. The first presenter is here. So the first presentation is, as you can see, has the name 10T SRAM cell as in a memory computing engine for a large range of Boolean computations. The authors are Mr. Kumar, Bing, and Gupta from India. And I think the presenter is Mr. Kumar.
Yes, sir.
Yes, thank you very much. Mr. Kumar, you have the floor. Thank you very much.
Okay, sir. So, should I proceed?
Yes, of course. Thank you very much. Yes, of course. Thank you.
Okay, sir. So today I will give a presentation on 10T SRAM cell as an in-memory computing engine for a large range of Boolean computations. So these are the overall structure of the presentation. First, we will have a look at the general introduction, followed by literature review, then earlier used methodology, followed by proposed work, and then simulation results and differences. So first, let's have a look at the introduction. So in today's world, we very well know that today's world are using von Neumann architecture or the Harvard architecture. But the problem with both the architecture is that data needs to be continuously shuttled back and forth between the processing and the computing units. So what I mean is that suppose there is some data here inside the data memory and I want to process it, suppose to perform any Boolean computation. Then first we have to give the instruction to this memory and then data have to be read into the ALU, then perform the operation, then store it back into the data memory. So this is the whole overall architecture of currently used technology. But there is certain problem with it, because it leads to huge energy consumption. For example, if we want to process huge amount of data, especially in the field of AI, where a huge amount of data needs to be trained and processed. So for those applications, we cannot employ such architecture because it will lead to huge bandwidth requirement as well as energy requirement. So to overcome, so this is the well-known the bottleneck problem. So those von Neumann architecture creates the bottleneck problem because the limitations, the bandwidth of the this transmitting medium is fixed. So we cannot transmit any data at infinite speed, at infinite bit rates. So there is a bottleneck. So we cannot. There is certain upper cap on the data transfer rate. So there is computing limitation due to bottleneck problem in the fields of this cloud computing, artificial intelligence, sensor network, and DSP processor, and many more. All these fields are huge data hungry fields. They need huge amount of data. So to overcome such problems, people have come with the modern approaches such as in-memory computing. So in in-memory computing, the computing task is performed within the memory computing units itself or within its periphery. So we save the bandwidth, there is no need to transmit the data between computing code and the memory and the computing code. So we preserve the energy as well as the bandwidth. So how do we do this? Let's have a look. So suppose there is this is a conventional way. The first is the conventional way of performing the data. Suppose there is some huge amount of data inside this memory. First, the data have to be bring back into this ALU. That certain operation needs to be performed depending on the requirement. Then it needs to be stored back into the memory. So as we can see, it will require huge amount of time, bandwidth, energy, and all. So what this is the modern approaches. So we can avoid such transmission by just signaling our memory intelligently and configuring our memory so that the computation can be performed within the memory itself. As we can see, there is no need to transmit huge amount of data. Only we are giving the signal to our memory, and all the required operations such as Boolean operation or any arithmetic or any other operation can be performed within the computing unit itself. So it saves huge amount of bandwidth as well as energy. So, but the problem with the previous proposed technology was they were able to realize only the standard logic. For example, NOR, XNOR, or AND. In most of the cases, you can see they were able to perform only standard operations. Suppose if we want to perform some arbitrary operation like A bar B, suppose CD bar, like this kind of thing. So they were not able to realize such a Boolean computation within the memory itself. So in this, what we here also you can see all the papers only standard logic are being realized within the memory. So to overcome that, we have proposed our work. So okay, first let's have a look at the methodology used earlier. Suppose there is, suppose first case we are assuming there are two memory cells. First, this corresponds to QA. Suppose, and this it corresponds to QB. So suppose 0, 0, these memory cells are storing data 0. So we can see that here, if we apply WL1 line, signal somewhat pulse like this, and WL2 pulse like this, then after discharge operation, because first the operation is to charge this both BL and BLB line, which is the standard operation of any memory cell. So after discharge operation, we can see that if the voltage is below certain threshold value, then it can be decoded as 0 BLB line, and but for BLB line, the voltage is greater than the threshold voltage. Here it corresponds to BLB line, it is greater than threshold, so it can be encoded as 1 here, and here it is below this threshold voltage, so it can be encoded as 0. Similarly, for the second case, both the lines will discharge one by one. So it is 0, so it will discharge here, it will discharge from here. So both, but still both are above the VDS threshold line. So both can be encoded at once. Similarly, for the case of 1, 0 and 1, 1, we conclude that at the end of the operation, an OR logic can be realized on VBL line, and a NAND logic can be realized on VBLB line by setting the threshold voltage. So this is the whole overall structure of in-memory computing. So what we have done, as we can see in the previous, all the proposed in-memory computing architecture, they were using a single WL1 line. And so what we have observed, these were the main limitations, that we were not able to perform any arbitrary logic like A bar B, as already discussed in the previous architecture. So what we have done in our proposed architecture, we have provided two different this read word line bar and read word line, these two different lines, so that this both A and A bar can be individually realized. How it can be realized, we will have a look now. Suppose we want to realize the A bar B and operation within our memory. So what we have proposed on this line, if for A bar B means none of the operand is in complemented form, A is also in, as it is not in complemented form, B is also not in complemented form. So if we will signal WL1 line high and RWL2 line high, then we can realize this AND operation, because only corresponding to one case, the output is high on this RBL and RBLB line, and for rest of the cases it discharges to 0. So we can see it can realize here Y equal to A B operation here. Again, so this is the first step. First is the precharge step. For any memory operation, we need to first precharge this RBL line, bit line. Second one is the memory read operation. For memory read operation, we are turning on this WL1 line high here. You can see it is high, it is 1, and this WL bar line is 0. Again here WL RWL2 line 1 is high and the RWLB2 line is 0. So corresponding to here, it suppose we can understand in this way that it corresponds to A and it corresponds to B. So the output of this two signaling will give Y equal to AB. So third one is the bit line sharing. On this, turning on this phi1 this on equal to 1, then we can get the final operator Y equal to here, but it's on Y equal to AB. So next, consider realization of A bar B. As already discussed, here the A occurs in the complemented form. So we have turned on RWLB line 1. It is so it will correspond to A bar, and here it is correspond to B because RWL line is 1. Here RWLB line is 1. So combining two, we will get A bar B Y at the output. As you can see, for only 0 1 output which corresponds to A bar B, so we are getting the output as high. For other rest of the cases, we are getting the output as 0. So in this way, by using decoupled read word lines, as opposed to previous case where we are using a single RWL line, we can perform any arbitrary operation within the memory itself. Similarly, we can perform any SOP form structure also from previous set of discussions. As you can see for A bar B, again here this RWLB line is kept high, so it corresponds to A bar, and here RWL line is high, it corresponds to B. Here also similarly, here it is C and it corresponds to B bar. So combining these two, we can get this our required output. So this is the flowchart algorithm, algorithmic flowchart of how our proposed algorithm will work on in memory. So first, obviously, we will be given or we need to compute the SOP form of any required Boolean logic. Then, if any operand occurs in complemented form in meantime, then if yes, then we need to turn RWLB line high. But if does not occur in complemented form, then we need to turn RWL line high. So in this way, then after this turning on this phi1 is actually the tertiary line, this line. So after performing this operation, we will get our desired output. So, but this is a simulation result that we have got an LT-SPICE widely used simulator. So we can see we will also perform the Monte Carlo simulation for PVT to incorporate the PVT variations. This refers to the process voltage and temperature variations. As we can see, this red rectangular box shows our output where it's 1. So we can say for the case of 1 1 only the output is giving 1. For rest of the cases the output is of both the lines RBL or RBLB, it is 0. So it's giving the our desired output. So this is a Monte Carlo simulation performing. We have taken a 30 millivolt sigma variation in threshold voltage. So this is a process variation, and then voltage variation of 100 millivolt, which is 10% on nominal VDD because we have taken 1 volt as nominal VDD, and for 4 different temperatures. So we have incorporated all the 4 PVT variations in this table, and still we can see that our voltage required voltage table is acceptable because it's 0.5 is somewhere here, so it's still very much above around the 0.5. So it's giving 1 only corresponding to last case of case 1 1. For all the other cases, it is giving output as 0, which is the required output of Y equal to AB. So again, for Y equal to A bar B only corresponding to 0 1, we are getting the output as 1. So again, to demonstrate the capability of our proposed device, we have shown it on 3 variables. Again, for 3 variables, also it gave our desired output. Only for 0 1 0 it gave the output high. For all the other output, both the lines were at output 0. So only corresponding to this input, we will get the output as high. Again, to show that our device can perform any SOP form realization also within memory. So we have tested it on this Y equal to A bar B and B bar C. Here also it gives 1 on the desired output. For example, for 0 1 here it's is 0 1 corresponding, and similarly we can check it will give the desired output. So these were our energy and delay analysis. The latency was found to be quite a little bit high because obviously we are performing 2 level of discharge mechanism, as I can show you. We are actually we are here operating the bit line chaining operation followed by this phi2 line to get the output here on the capacitor. So the delay were found to be a little bit high compared to previous operation, and energy also because we are using 20 transistor and previous architecture was using at most 80 or 90 transistor. But the advantage we are getting is that it can realize any logic operation, any logic function in SOP form, which can be either complemented or in uncomplemented form. So these were the main advantage that we got from our proposed architecture. So these are the differences. So that's all from my side. Thank you.
Yes, thank you very much for the presentation.
Thank you, sir.
Yeah. It really comprises apart from several parts of computing engineering. It's very interesting. So please, questions from the audience, please. Probably people who are familiar with this region of computing engineering.
Hello, sir. Yes, sir, I didn't get it.
No, I'm just waiting for possible questions from the audience, and since I don't hear questions so far, can I ask you once again, please, since I'm not expert in this region, in this area, can you tell us in brief some advantages or disadvantages of this computing architecture of in-memory computing architecture as compared to other, let's say, more traditional techniques? Can you tell us some advantages or disadvantages?
Yes, sir. Sir, actually, this, as I have already told, the advantage is that all the previous architecture, in-memory computing architecture, they were not able to perform any arbitrary logic in, suppose in uncomplemented or uncomplemented form. So that was the part of in-memory computing. But coming to standard digital logic for all these designs, actually the hardware requirement is very high. And again, if we want to perform it on any standard logic that is built inside the ALU, again, that will be the problem of bandwidth and that energy requirement, because we need to first read the data from the memory, bring it into the ALU, then perform all those operations, then store it back into the memory, because this is a well-known traditional volume architecture. But there is again a bottleneck problem, and it is also creating a lot more problem in recent areas of neuromorphic computing, where we all know huge amount of data needs to be trained or processed. So it's not possible to bring such huge amount of data into the ALU again and again, then train it again and again and store it memory. So this in-memory computing is much better option for this neuromorphic and neuromorphic applications.
Yes, thank you very much. Thank you very much for very nice discussion. Once again, if there are I don't know if there are more questions from the audience. I don't hear more questions. Thank you very much for the very interesting presentation and work.
Thank you, sir.
Thank you very much. And so let us proceed to the second presentation, which has the title "Application of VFD for Power Factor Improvement in LED Loaded Power Distribution Lines." The work is by Mr. Svinkūnas, Petrauskas, and Petrauskas from Lithuania. And I don't know, the presenter might be Mr. Svinkūnas from Lithuania, please.
The presenter will be Mr. Petrauskas. We discussed between.
Oh, thank you very much. Thank you very much. Thank you very much. Thank you very much. Yes. So please, you can share the screen. You can share the screen in order to make the presentation, please. Thank you very much. Thank you. Oh, unfortunately, I cannot hear anything. Unfortunately, there's a problem. I cannot hear the voice. Some technical error, perhaps.
Hello, do you hear me now?
Yes, thank you very much. Excellent.
Okay,
Thank
hello,
you.
everybody. So the topic of my presentation is too long, so I'd like to emphasize a few words. It is the variable frequency drives, reactive power, and LED lighting devices. So I would like to begin from the comparison of the Sorry, something wrong with my presentation. Just a minute. Okay.
Yes, of course. Yes, take your time, please. Yes. Oh.
Yeah. I would
Yes,
like
thank you.
to present and make the comparison of the two lighting bulbs everybody have at home, and I hope that everybody replace the conventional Edison bulb to the lighting emitting diode bulb. Which is better? Of course, the LED bulb is better. It produces, it consumes less energy. It have a better lighting spectrum, the longer, less time. But what from the point of view of input current and reactive power? So the current of the conventional lighting device is quite sinusoidal, no harmonic distortions, no reactive power. But if you can watch to the current of the LED lighting devices, you can see it produces a lot of the harmonics. It produces some kind of the reactive power. What kind of reactive power? I made some simple experiment by using power quality analyzer and using some conventional lighting bulbs, and can see that all the lighting bulbs produces the negative reactive power. We can see that from the vector diagrams, and also it can be seen from the table presented, from the data presented in the table that shows that all the lighting devices produces this negative power, even it is connected in parallel 2, 3, or 4 lighting bulbs. Does it cause any problems at home? I suppose to be no, because of this very small power of the lighting devices. But in case of the wall screen in the sport arena, 32 kilowatts wall screen in the sport arena, it causes the problems. Why it causes the problems? This comes from the conventional and nowadays power distribution lines. In the conventional power distribution lines, we have loads as the induction motors. It consumes the reactive power. It consumes the positive reactive power. For the reactive power compensation, it usually was used the capacitor-based compensator devices that produces negative reactive power and push the reactive power of the power distribution lines close to zero, a very good power factor. In the nowadays, we have a quite different situation. The power distribution lines are loaded by lighting devices that produces negative reactive power, variable frequency drives that produces negative reactive power, and also we have left it from the old days the compensator, which produces the negative reactive power else. We got the sum of the negative reactive power, very bad power factor, a lot of reactive power in the power distribution lines. That situation we can see from the data presented in this table, taken from the power distribution lines in Žalgiris Sport Arena in Kaunas. We can see that production of the reactive power is much bigger than consumption. That means that a company exploring this sport arena pays fines for the reactive power to the company of the power supplies. How to solve this problem? We would like to present 3 ways of the problem solving. The first way, to bypass variable frequency drive. Second way, by modifying conventional variable frequency drive. And the third way, by replacing conventional variable frequency drive with the novel matrix converter based variable frequency drive. So why the first way of the computation works? Because the induction motor It's a lot of induction motors installed in the sport arena. They are used for the fan powering, for the pump powering, and all the induction motor produces the positive reactive power. By bypassing the variable frequency drive and connecting the induction motor directly to the power distribution line, the induction motor could compensate the lighting power produced by LED lighting devices and get power factor quite to the 1, close to the single, and let the reactive power quite to the 0. The second way, by modifying conventional variable frequency drive. The conventional drive consists of the rectification stage and inverting stage, and it has the intermediate DC circuit with some capacitors for the filtering. By upgrading some equipment and putting more capacitors in this circuit, we can use it as reactive power compensator. To prove this, I made some simple experiments. First experiment consists of the research of the situation of the conventional single-phase rectifier and capacitors banks. Got some results. Result shows that by changing the value of the capacitance, we can get the leading reactive power at the point of connection to the power distribution lines and the lagging reactive power. This means that this device could work as a reactive power compensation. Second experiment consists of the rectification equipment and lighting like the LED lighting devices connected in the parallel. Also, we got some results, and results shows that rectifier could compensate the reactive power. We can get reactive power equal to the 0 at this point. It means that it works as a reactive power compensator, but in case of the big amount of the LED lighting devices, it doesn't. And the third stage of the experiment, I use the conventional variable frequency drive, put some upgrading equipment to the DC circuit, connected some amount of the LED lighting devices, and got some results. The result shows that this variable frequency drive with the upgrading equipment can operate as the reactive power compensator at the same time providing this main function, motor powering and motor speed control. And it can be seen from these diagrams that this variable frequency drive can produce positive reactive power, can produce negative reactive power, and can make a reactive power at the point of the connection to the power distribution line equal to the 0 at this point and at this point. And the third way of the reactive power compensation in the sport arena is to replace the conventional variable frequency drive with a novel matrix converter based variable frequency drive. The matrix converter based variable frequency drive do not have the intermediate DC circuit, but it consists of the 9 bidirectional switchers, which converts the AC in the input to the AC at the output. This allows to implement indirect space vector modulation, and this method control allows to directly control the angle between the current and the voltage of this converter connection to the power distribution line. And it allows this drive to directly control the reactive power. So in this way, it works as reactive power compensator because the LED lighting devices produces negative reactive power to the power distribution lines. The matrix converter based variable frequency drive can take its reactive power and makes the reactive power in this point equal to the 0. This way of compensation I tested in way of MATLAB simulation. For the simulations and reproducing of real current of the LED lighting devices, LED lighting device presented in this figure, I used appropriate number of current sources and reproduce accurately this type of the current with the same amount of distortion. For the matrix converter based variable frequency drive simulation, I used 9 blocks that implemented the bidirectional electronic switches and some control equipment to implement enduring space vector modulation. And got some results. The simulation results shows that the variable frequency drive based on the matrix converter could produce lagging, it means positive, and leading, it means negative reacting power. It allows it to work as a reactive power compensator. But not everything okay. By the changing current displacement angle to make reactive power leading or lagging, the voltage on the motor's stator windings does not stay the constant. By increasing current displacement angle, the voltage gets smaller. It doesn't matter on the positive side or on the negative side. To solve this problem, we need to change the modulation index of the inverter side and to make some modulation index manipulation zone wider. We need make some connection, change the connection of motor. Instead of connection in the star, we need to connect the motor in the delta, and it makes the wider range of the manipulation for the modulation index. In this case, we can keep voltage on the motor starters windings constant, opposed in the case of this situation when the modulation index are kept constant. So the simulation results shows that by using 5.5 kilowatts matrix converter based variable frequency drive, it could compensate the reactive power produced by the 32 kilowatts LED lighting device. The conclusion, the conclusion presents actually the topics I showed before, so I would not waste your time by reading this conclusion. Better go to the question. The question, please.
Thank you very much. Questions from the audience, please.
Here is Peter Braciník from Žilina.
Yes.
Can you hear me?
Yeah.
Yes, of course. Thank you very much. Yes.
Thank you very much for the nice presentation. I'm not the expert in this field, but what took my attention was that did you test it, this power factor correction at the operation of these asynchronous synchronous machines controlled by this matrix or normal converter in the situation when the operation of the motors is not smooth?
I do not test it experimentally this way of the
in simulations.
No, I only they're tested by MATLAB simulation only in the steady stage.
Okay.
Not when the motor operation is smooth.
Yeah, but it's good because generally we expect this machine to be in this steady state operation if everything is okay. So that's probably the main idea. That
I didn't test it in smooth.
Okay, thank you very much.
Thank you for question. More questions, please.
Yes, other questions, please. Okay. I'm afraid that we don't have more time. Thank you for a very interesting and very advanced level presentation in this particular area of power engineering and LED stuff in high voltages, high power circumstances. Thank you very much for the interesting presentation. So, thank you. So let us move to the third presentation, which has the title Advanced Switchgear Signals Simulator for a Distribution Substation Model by Mr. Höger, Mr. Reguľa, and Mr. Braciník in Slovakia.
Yeah.
Is the presenter? Yeah. Oh,
I'm here. I will present.
Yes, thank you very much. Thank you very much.
Okay,
Please share the screen. Thank you very much.
Yeah, I will try my best to share the screen.
Yes, of course. Yes.
Just a second.
Yes, thank you very much. It should be in the bottom and center of the bottom line in the center. Yes. Take your time.
Okay.
Excellent. Very good.
Now you should see. Now you see the presentation. Okay.
Yes. Exactly. It's very nice. Very nice. Thank you.
Okay. So thank you very much. My name is Braciník. I'm from University of Žilvinas, and I would like to present our paper with title Advanced Switchgear Signal Simulator for a Distribution Substation Model. Unfortunately, Mr. Höger, my colleague who should have presented this presentation, has to go somewhere else, so I will try my best to present his ideas. First of all, I would like to tell something about the motivation. Nowadays, in power system engineering, we face the new or improvement of switchgear devices. We face the digitalization issues, and so the requirements for young power engineers as well, the staff that is already hired and work for power system operators or distribution system operators, had to be educated to be familiar with new protection devices, with new switching devices, and so on. So it's a complex issue. The problem is that it's very hard to come to real power substation and to take half of it for just education purposes, because normally it's used for electricity distribution and transmission. Therefore, it would be really nice to have some other tool on which these people or students can practice and teach new stuff about switching processes, communication between digital relays, the communication between the switchgear and the digital relays, and so on. Therefore, there was an idea at our department that we would create such a testing lab or some tool for students and for some industry people. We are in the middle of, we are doing in the project, and we are in our last year. So in these photos, you can see how it looks like in the laboratory. On this big picture, this is the tableau where there is five bays, visible 5 bays with digital protection from ABB, and here are some switching devices or some tools representing normal switching device in power substation. We have also one very special switchgear from ABB, originally created for us in Brno, in Czech Republic. So there are normal parts like low voltage control circuitry. There is a high voltage circuit breaker, these connectors. What is very special one that is open, we can interfere with the installations, and there are some special parts for students that can see what's going on inside the switchgear. This is the schematic layout of the power substation that is modeled in this laboratory. It has 2 bus bars connected with 2 bus couplers. One of them will be represented or is represented by this real switching device. The other ones are simulated by the tool I will present later on. So we have basically three main types of feeders or bays. The one is the bay coupler. The other one, maybe the most complicated one, is bay represented by a transformer bay. It means that this part where the transformer to the substation is connected and the energy is flowing inside the power substation. And then we have four bays representing power lines feeders. This is the view of the back side. On the left side is the back side of the tableau. So here you can see the back side of the digital relay. Here are some interfaces with control system, and here is the low voltage circuitry. And here you can see some switching devices, low voltage switching devices that are representing the switchgear. So our idea was to create a circuitry that is very close to the one that is used in normal circuit switching device, in this circuit breaker device. So the students can face how it looks like in normal life, in normal power substation. And when trying to learn either to connect or to put the connection to the correct form, according to the documentation, or to find a fault somewhere, or to add some measuring devices, so they can have a touch of real life, even if it is a laboratory. Here is the simulation tool for simulating the switching devices I would like to present in this paper, or the main part of this paper. What is going on? But before it, I would need to say that we try to be as realistic as possible, even in the laboratory environment. So as I said before, we have, unfortunately, only 3 real track bus circuit breakers, and the rest of the switching devices has to be simulated. But nevertheless, the circuit breaker that is in the real switchgear is connected to the simulation device, and these other 2 circuit breakers that are just separately installed or placed in the laboratory will be integrated as well. So the interface that will be created for students will be connected with them, so the students will manipulate with real switchgear as well, not only by simulated. Here is the presentation of basic requirements for the simulation of the switchgear. We have basically 2 main feeders, the transformer feeders and the power line feeders. And here are some sum of signals and number of input-output requirements. The most complicated bay is for the transformer. It consists of 2 circuit breakers and 4 disconnectors. And here are some representation of signals that are connected to the specific switching device. Disconnector with the everything switch. So they have 2 signals for state signalization, relay control, open close command, and locking management. So we try to be as accurate as possible, or to represent the real life or the real description of real devices as much as possible. Circuit breaker is more complicated. Oh, sorry. So here, state signalization, spring charger, activation or activity. This is some protection against the faulty switching, and that is simulated relay control, open close command, and closing call command. Summing this together, there is 20 binary inputs and 24 binary output that must be simulated. And the logic level for these inputs were taken for 24 volts DC for 2 reasons. The first one is safety reason, because when in the lab and there will be students dealing with this, and the second one, that this is normal voltage used very often in power substation for such circuitry. So again, the students or the practitioners will face the real situation like it is in real power substations. Here is the layout or hardware setup of the simulator. It's hardware part. It's based on Arduino Uno Mega Pro. We were looking for low cost solution, because it has to face students. Students used to tend to make mistakes. So if something is burned out, we can very easily replace it, and the cost will be not so expensive. So here are the specific part. The first one is the Arduino. Second one is power supply feeding the Arduino Uno and also some input-output circuits. Number 3 is binary input board. It's a conversion for 24 volts that is used in switching switching relays and digital relays to 5 volt logic that is used for Arduino. We used the voltage dividers. There are some problems with it, but at the moment we are working on other solution, but at the moment this is the most suitable one. The number 4 is output board. So there is a amplification of 5 volt DC signals from the Arduino to 24 volt DC level. That is manageable by protection relays. Very important was as a small footprint, so it must be a very small device, because as mentioned before on this picture, it is placed here, so there is no much space. This is the representation of one bay, and our idea was to make it as small as possible but functional, to put it on the back side of the tableau. Coming back, this is the representation of the software. Generally, the software was created in C++ using the Arduino framework and is object-oriented architecture. The main object is switch class, which has one subclass called drive class, and this drive class have 2 possible subclasses: is motor drive and spring drive. Motor drive is representing the drive of the disconnector, and the spring drive is representing the drive and for a circuit breaker. The reason for this separation is that I don't know if you are familiar with these mechanical issues of disconnectors and circuit breakers, but circuit breakers are usually use the energy that is stored, if they are electromechanical, that is stored in torsion of iron bar or spring, let's say spring. And the reaction is very fast. It's due to the reason that if there is some short circuit and the circuit breakers should switch off the faulted currents, the opening of the circuit breaker must be very fast. So there is no place for a conventional motor, but it must be made by this energy that is stored in the torsion of some spring or some metal bar. So the activation time is very, very quick and very fast, and also the action of this switching on and off is very fast. On the other hand, there is unlimited energy that can be stored by this torsion. So we wanted to simulate this effect that so this class is representing the small time of activation or activity when the switching or closing is activated, and in the same time it controls the energy that is stored. If you make too much switching operations with the circuit breaker, you will lose your energy that is in distortion, and you won't be able to operate the circuit breaker anymore until you use some motor that will make this torsion again. Despite this motor drive class that was created for disconnector simulation, there is a conventional motor that is opening and closing the disconnector, so it can take from several seconds up to tens of seconds or 100 seconds. So the time that is needed for closing and open a disconnector is much higher than the time that is intended for circuit breaker operations. All the logic is based on state machine diagram. This is, for example, representing the control coil class, meaning that it's inactive state. If there is a binary output saying that it should be closed, so it's activated, and then there is a calculation at the back in the software calculating if the time of the signal present saying that it should be closed or change the status quo is long enough. If there is a long enough, so it is evaluated like the command is real, and it will change to the state of active. If the time of the signal saying that it must be active is smaller than the predefined time, it will come back against to inactive state. So this was aimed to simulate the real operation, that the time of the signal that is presented on the input input ports of coils must be present long enough for the evaluation that it is real and that the operation should really be activated. If in active state, if the signal comes to switch off, so it will change to the state of it will be deactivated and it will change to the state inactive. This is the state diagram of the generic drive class. I will start in a closed state. If there is this drive is in closed state, when there is a signal saying that open coil is active, so it is true. So it will change from the closed state, from the idle position to the moving position. So it start to move, and it's the position for specific time that it's opening. When it reach, there is a control that it will simulate in the background that the moving of the contact, either of the circuit breaker or of the disconnector. For sure, in the case of the disconnector, it will last much longer. So the system will signalize that now I am in the middle, somewhere in the middle of this moving. So you have to wait for the device to reach the opening or close position. In the case of circuit breaker, it's very fast. But if it reach the final time and it's changing the state to the open, then when it is open, it's idle. Okay, it's open. When there is a command to close the coil, it will again start its procedure, but in opposite direction. So it's signalizing that it's closing. When it reach the time for closing, it's closed. It's the same as by the opening. So the idea was to simulate this open and closing times to teach the students and the staff that it's absolutely different for for circuit breakers and for disconnectors. So software capabilities. With this one setup, with Arduino setup, we can simulate up to 4 disconnectors and 2 circuit breakers. We can simulate adjustable drive speed. It means that the different opening and closing times for disconnectors and for circuit breakers. So it will produce or simulate realistic operation times. And we have 2-bit state signalizations. So it will check the status quo of the connection and disconnection of both sides of the contacts. This is something that is used in real life as well. We can model the control of coil activation times and hardware-based interlocking using blocking coils. It means that we can learn the students to deal with these aspects. So if the process of switching on and switching off is not done correctly, it won't be done either. So it again represents the real features of real switching devices. We can model the limited switching capability of the spring drive, as I mentioned before, recharging of the spring necessary after several switching operations. So the student can learn that we cannot do as many switching operations as we wish, but we have to count with real energy that is stored in the real switchgear. And the last is the optional anti-pump function of the spring drive. It means that there is if there is some problem with different signal coming to the input ports of the coil, saying that you have to switch on, switch off, switch on, switch off. So this is also detected and eliminated. It is again as it is in a real switchgear. After doing the prototype,
I'm sorry, Mr. Speaker. Well, please, in 1 minute, if we can conclude in 1 minute, because
yes, I can. I apologize very quickly. We made the measurements of real. We made the prototype and we make the measurements. Here is very quickly oscilloscope record of signals. So this is for disconnector. Coil activation 40 millisecond. Transition time was set to 1000 millisecond. Measurement. There was a signal to close. So it takes some time, and then the open signal changed to 0 and the closed signal changed to 1. It took 40 milliseconds for activation and approximately 990 milliseconds for transition time. What was confirmed the real operation or correct operation. Here is for circuit breaker. It's the same situation. Activation signal changing from open to closed. in small, because 20 milliseconds for activation and 40 milliseconds for operation. Measurement was like this, so it's within expected value. So the simulation and the real testing confirmed. Unfortunately, I don't know if I have 1 minute and this is work, but this is the video saying that, showing that how it works. So this is the circuit breaker closing, so it was immediately done, very shortly, and this is the operation of closing the disconnector, so it will take more time. Green light means that it was, I hope I'm still on. So it was operating correctly, and it was communicating with the protection relay. Thank you very much. Thank you. Sorry for being too.
No problem. No, thank you very much. No problem. Some questions from the audience, please. I think we are a little bit late from running out of time. Thank you for the very interesting presentation. By the way, how much if you permit, how much is in this substation? What typical voltage of these substations? Typical numbers for voltage, if you permit me a quick question.
We are simulating this on distribution level. It can be 22 kilovolts or 35 kilos, depending on the state, on habit. On transmission level, it could be 110, 220, and 400 kilovolts.
Yeah, thank you very much. Thank you very much, and for a very interesting presentation. Now let us move to the fourth presentation, which has the title Wireless DBS and Blood Pressure Measurement System for Experiments with Animals. The authors are Mr. Jonkus, Mr. Chomanskis, and Mr. Danielius from Lithuania.
Hello, everyone.
Thank you very much.
The work I am going to present has two parts, medical and engineering. The medical objectives of your work are to investigate the ability of your caudal ventrolateral medulla to stimulate the influence blood pressure in freely moving rats. The ventrolateral medulla is the brain region, more precisely is the part of the brain stem, which plays a major role in regulating blood pressure and breathing. Although the targeting neural centers in the medullary region considered dangerous and prone to complications, it could open a new perspective to treatment of drug-resistant hypertension. The engineering part of your work is about designing the device which is capable of performing deep brain stimulation, or DBS for short, and measuring blood pressure in freely moving rats. My presentation is focused on this part. There are 4 types of experimental DBS systems in use today. The first type experimental DBS system, and still popular today, were external, attached with wires to a rotating twister or swivel connector at top of cage cable, or transmitting electrical impulses and at the same time allowing the some rats movements in the cage without breaking or twisting the wires. More recent DBS systems have been miniaturized and fitted on the animal using special backpacks or jackets that hold the stimulator and the power source. Usually no more than 100 grams could be added to the backpack without causing a change in behavior of an animal. Yet another type of DBS systems use stimulators that are small enough to be fitted on the animal's head. Usually no more than 25 grams of weight could be mounted in such cases. The 4th type of DBS systems are very miniaturized and can be implanted under the animal skin. Among the current commercial DBS systems, just a few designs have integrated sensors available. But as far as we know, there are no commercial DBS systems with blood pressure measurement. The device we need for experiment must be wireless, because the wires connected to animal significantly influence its behavior and thus influence the results of the experiment. The device must be capable of generating deep brain stimulation pulses and measuring blood pressure. For our experimental device, we chose a low-cost and easy-to-use Wi-Fi model from Expressy Systems with ESP8266 chip inside. This is all-in-one model with Wi-Fi communication. The ability to program ESP8266 from the Arduino environment and well-prepared TCP/IP communication libraries makes it easy to use in wireless data transmission applications. ARM Cortex M0 microcontroller was used to control blood pressure measurements and brain stimulation. The blood pressure measurements circuit consists of an external analog to digital converter and pressure sensor, which is designed to be used in wet applications. The stimulation circuit is explained in the next slides. DBS is a technique that stimulates deep-seated brain nuclei. Since its introduction, this technique has become one of the most effective treatment options for patients with advanced Parkinson's disease. The exact mechanism of DBS is still unsettled. On the slide, you can see some examples from literature, but it's not complete list. Different waveforms and different contact arrangements are used for different purposes. But there are a few things in common. From an engineering point of view, the DBS pulses are electrical current pulses, and these pulses must have charge-balanced form. The amplitude of the pulse must not cause brain damage and therefore limited to about 200 microamperes. In our device, we use this DBS pulse waveform. The pulse shape is full software generated and can be programmed to any form. During the experiment, we varied only amplitude, duration, and pulse and repetition period. Voltage to current conversion is performed by classical circuit having an operational amplifier with negative feedback. The current flowing through resistor R2 is proportional to a voltage in the non-inverting input. The actual voltage to current conversion circuit have additional elements: digital to analog converter, which acts as voltage pulse generator, resistor connected in series with a brain resistance. The voltage drop across the resistor can be recorded by microcontroller, and the actual current can be calculated from Ohm's law. We used current pulse recordings for remote monitoring of the stimulation process. For example, there were quite frequent situations when the rad broke wires. Such situations were easily detected remotely from current pulse recordings. The generated DBS pulses are, as you see in the slide. Figure I is an oscilloscope recording on the 1 kilo ohm resistor connected to the current pulse generator. Figures B and C represent current values calculated from Ohm's law when voltage recording was obtained with an onboard ARM microcontroller. Noisy curves in figures B and C represent well-known fact that microcontrollers' internal analog to digital converters are of poor quality. The current pulse recording capability was used only to remotely check the DBS process if the process is going well. On this slide, you see a rad during the experiment with a device and battery attached to its back. The total weight of the device and battery was 55 grams. In order that the weight does not produce stress during the experiment, rats were trained to carry weights before experiment. The communication with device was carried out by the service running on a computer in local network. The service was designed to efficiently acquire the raw data from a sensor and pass the data to the broker service for further processing. The developed service was engineered to manage large volumes of data and continue to function even in the events of failure or errors. The active MQ was employed as broker servers for message exchange, allowing the efficient data transfer between the sensor and the data analysis pipeline. Node-RED, a flow-based programming tool, was utilized to create dashboards for manual sensor control, such as adjusting the recording period or configuring the stimulation waveform. Each device generated up to 100 data points per second. Historical database was employed to alleviate the load of real-time data storage and processing. This approach allows to efficient data management and analysis while preserving the system's real-time nature. Historical data is primarily employed for in-depth analysis and simulations. A daily data transfer job was responsible for transferring data from real-time and historical databases. This job also manages the removal of data from real-time database to maintain the optimal balance between real-time nature of the system and the storage capacity. To store the acquired data, PostgreSQL database was used for both historical and real-time storage purposes. In this slide, you see 10 seconds of data segment. A gray curve represents raw data from pressure sensor. Sample rate was 100 samples per second. Heartbeat rate produced blood pressure variations are clearly visible. Rats have a heartbeat rate of about 6 beats per second. The signal contains pressure variations caused by respiration. This is black line. Here, the blood pressure measurement for 12 days period is presented. On day 4, the DBS stimulation was initiated and about 15% blood pressure drop was observed. Stimulation amplitude was far from the maximal value. The DBS amplitude was switched on for almost the maximal value for a 3 minutes interval, and the huge blood pressure drop was observed. And when conclusions, sensor model were equipped with 2000 milliampere hours lithium-ion battery, which provided power for about 20 hours of continuous measurement without power savings. Data collection lasted continuously 24 hours per day for 2 weeks. 80% of animals with electrodes implanted in the lower medullary region had survived in the experimental period. 60% responded to stimulation with a noticeable decrease in blood pressure. Thank you for your attention.
Yes, thank you very much for the presentation. Questions from the audience, please. If there are not, I don't hear some questions now. I can ask you what are the possible usefulness of these biological studies, possibly for some biological investigations.
This is primarily goals is medical goals, and in perspective, it's one possibility of treatment of drug-resistant hypertensions or drug-resistant.
I see. Yes, and of course you can. Of course, I'm sure that you are taking care of the safety of the animals. I don't know. Some comment on that. So perhaps by reducing the transmitted power or whatever measures to take care of the, I don't know if you have a comment on that, of the safety of the experimented animals, perhaps by reducing the transmitted power, or I don't know, or the voltage applied. If you have any comment on that, yeah.
DBS stimulation was not caused injury on the animal's brain. If you're asking that.
I'm sorry, I missed that. Can you repeat, please? Yeah, I'm sorry.
DBS stimulation not caused injury to animal.
I see. Very good. And I'm sure that the very many measures to to ensure that, like reduced transmitted voltage or the reduced voltage of battery, and to know, I'm sure that you know very well the ways to reduce the risk. Yeah, thank you very much. Other questions, please? Other questions? So I don't hear other questions, so let us move. Thank you very much for your presentation, and which involves, of course, a lot of electronics on that, and is very interesting. And the final presentation is the final fifth presentation. Here's the title: Semantic Segmentation Using UNet Deep Learning Network for Quince Phenotyping on RGB or and Hyperspectral Images. The authors are Mr. Suders, Mr. Narmetevs, Mr. Nikulins, Mr. Balsas, I'm sorry, Mr. Astil, Mr. Strautina, and Mr. Kaufman, and finally Mr. Calvin from Latvia.
Yes, good day to everyone. Can you hear me?
Yes, thank you very much. Fantastic, very good. You can share the screen. Thank you very much. Thank you very much.
Yes. So, good day to everyone. I represent Institute of Electronics and Computer Science, which is located in Latvia, in Riga. So, as it was mentioned, the title of our project, our paper is Semantic Segmentation using UNet. It's Deep Neural Network Architecture. And we are using it for detecting and phenotyping quinces on RGB and hyperspectral images. So our objective is to develop a non-invasive machine learning based phenotyping model using like RGB and hyperspectral images to detect Japanese quinces from the field. So we are working with semantic segmentation models and also with object detection neural networks. But for now, let's just concentrate on some semantic segmentation models. So for semantic segmentation, we are using the UNet architecture. It's well-known architecture. And we are using it to create a pixel-wise mask to separate berries from the field around and also from the environment around. RGB and hyperspectral images, yes, we are using those. Immediately I can say that hyperspectral images have more information to analyze, so the system works better on those, more accurate. I can immediately say that. About UNet architecture, yes, our group chose UNet architecture because since the quinces will be very close to each other, this architecture will be perfect architecture for this purpose. So when the raw image is fed into the UNet, it will produce a output segmentation map, and it will work decently with very close fruits, different kind of fruits, not only quinces. For example, we are also detecting and analyzing raspberries. Yes, and this architecture also works really good with the same class. With the same class. For example, if the two quinces are close together, then it will work very, very good. We also made some modifications for UNet by introducing the batch normalization layer between the convolutional layer and the ReLU activation layer. The padding of 1 is also in use, in the convolutional layer to prevent downsizing of image. For capturing hyperspectral images, we are using Specim IQ camera. Using this camera, the image is of size 512 by 512, and well, obviously RGB images have only 3 channels, but hyperspectral images which we are using and which we are working with have 204 channels. So a lot of information to analyze. And the specific wavelengths can be used from these 204 channels for example, to estimate berry ripeness. Is it ready or not to be harvested? So each hyperspectral images in the dataset has wavelengths from 400 nanometers to 1000 nanometers. So the upper limit is a little bit more than human visible light. So we were able to achieve an accuracy of 63.33% for hyperspectral images and 70.22% for RGB images. Yes. So, wait. If we are speaking about practical applications, so it can be used in the future for the automatic harvesting of quinces by the robot or by the drone, for example. Actually, at the start of our project, it was a main idea of our group. And our future work will include a model for detecting the ripeness of the quinces, and we will be using the hyperspectral images specifically because it's well, more channels, more information to work with. Also, we would like to I would like to mention that we are creating publicly available. Well, we have already publicly available hyperspectral image dataset, and the quinces used for this dataset were grown locally here in Latvia, the Institute of Horticulture. This dataset could be useful, for example, for different kind of experts, for example, for making similar projects. Yeah. So, and more practical applications could be, so computer vision using RGB and hyperspectral images can be also used. Well, main application is to distinguish crops and weeds, distinguish between those two, and also can be used to assess the quality and the ripeness of the crops. For example, for farmers also would be could be for farmers to precisely target herbicide applications to reduce or use the right amount of chemicals and minimize the environment impact. Also could be pests and insects could be observed and eliminated in the process, and also water usage also could be optimized using this technology to assess plant water stress by analyzing leaf reflectance on the leaf or on the plant. So the model was evaluated by the different metrics. Jawar index, also known as the interaction over union, accuracy, precision, recall. Recall is a positive prediction compared to the ground truth. And we also used F1 score, which is a harmonic mean between the precision and recall. And at the end, finally, the loss is calculated for both the training and validation loss. And the best weights were saved for neural network. So about yes, we have this training and validation loss. It was in this slide, two graphs, as you can see. So for RGB data and for hyperspectral images, two graphs. So, as I mentioned before, that we work with semantic segmentation models and also with object detection models. Let's say two models were trained on the same amount of data, and better results is in object detection case, I would say. So it's harder to train semantic segmentation model than object detection model. But although it's easier to train object detection model than semantic segmentation, but well-trained semantic segmentation model provides pixel level classification, allowing for more detailed understanding of the scene. It can different between different parts of the plant, can be made masks for example, for the leaves of the plant, for the fruit of the plant, for the stem of the plant, and it can be identify specific plant, also diseases and pests also could be more easily identified. So I will say that object detection is used more for estimating of the plant localization in the scene. Also for understanding, is the plant ready to be harvested or not? Maybe also for pests and insect detection, but it's better to use semantic segmentation for more detailed information to detect diseases or something like that, let's say. So in conclusion, I would like to say that we have several conclusions. So since the dataset consists of hyperspectral images, which are rich in information, the model trained on hyperspectral image data was better in almost any of the metrics as compared to model trained on the RGB data. Frames per second. This is the only metric where the model trained on RGB data is better. So in testing phase, when we are trying to analyze the data, the RGB data is faster to analyze. There's less information. So the weights obtained after the training for generating pixelized mask was quite accurate on the case of the hyperspectral image data. These generated masks can be quite useful for the experts. This is the other conclusion. It could be very useful for the experts in order to get the dimensions of the Quinces, for example, for either different research purposes, or for example, to estimation of the yield, for example, and this model is quite good, but I will say that the model can be even more improved by adding more hyperspectral images to the already existing data set, and train the model on the you can train the model on more enlarged data. This is it for me, from me. Thank you. Any questions?
Yeah. Yes. Questions from the audience, please. Thank you very much. And questions from the audience, please. Yes, Mr. Asefi.
Can you hear me?
Yes.
Hi. Yeah. Hello. My name is Sajjad. I'm from Tallinn University of Technology. First of all, I really appreciate your good presentation. I have two brief questions. The first one is regarding the training of the algorithm. Is it happening in online mode or offline? First of all, maybe you had in your presentation, I missed. And the second one is regarding the practical application. You showed that it would be possible to use for quadcopters. I was just curious to know if the airflow that is made with the rotors of the quadcopter maybe would affect the accuracy of the measurements. Have you tested it, or it's just the proposal to be tested? Thank you.
Yes, thank you for your questions. Yes, firstly, we are training our models locally on our servers. We have a GPU card A100, so one of the best, let's say, GPUs, and yes, that's how we train our models and also testing it. And for the second question, we have been testing this this system not on drones, but on the computers, like with camera, with phones. Can it affect somehow if we put it on the drone? If we put it on the camera on the drone? Well, of course, we have to take it into account and have some kind of stabilizers to either it's like for physical stabilizing the drone, or using some kind of software, but it can be done. It's like in our future work, we will work on it.
Great, thank you very much for the answer. Good luck with your research.
Thank you.
Yes, thank you very much. Other questions, please? So once again, let me congratulate you for the very interesting experimental research that you're managing. If you permit me a short question, so overall, is something promising out of this story? Something promising regarding good, for monitoring, I mean, for monitoring the quality of Quinces in this case, is there something promising in the horizon in terms of effective quality monitoring? Is the good progress for the practical results that you are waiting?
Yes, of course. It's quite promising, let's say, idea, promising technology, and we're as I mentioned before in my presentation, we are two institutes, and the second institute is from Agriculture Institute, and we are testing our technology there. and I mean it's working and it's quite promising. But we have to in future work we have to put this actually on the robot and some kind of automate this process by harvesting the fruits but now we are in detecting phase. We are detecting the Quinces.
That's very interesting. Thank you very much. Very interesting collaboration between agriculture perhaps department and your university. So thank you very much. Very interesting presentation also. Thank you so much. And with this presentation, we are exactly on time to have finished this session 11A on signal technologies. Once again, thank all the presenters for the very interesting presentations and quality work. So Darius, I have to finish the session. I don't know, Darius, if there is a closing ceremony for the conference.
So at first, thank you, Panayiotis, for your sharing, for your excellent sharing.
Thank you so much. Thank you so much. Thank you so much.
And now we have a 15 minutes technical break for voting and for summarizing results. And then we will back 15 minutes to 1 p.m. To the closing session, and we will say who won the prize. And I will say probably some words about participation level, and that's all. So we have a short break for 15 minutes.
Yeah. Thank you very much. Thank you very much, Darius. You will be back in 15 minutes. Thank you very much. Thank you.